Welcome to the computer security seminar. Today's speaker gave a talk about 2 years ago. He gave part one of this talk. Today he's going to give part two of the talk. Our speaker today is David Ford. He's going to speak about chaos, complexity, cybernetics, and Therminator. Dave.
Thank you very much, Sam. It's great to be here at Purdue, and it's nice to be here when it's not raining. Last time I was here, it was raining like crazy, and it's particularly nice in the spring. So lucky you guys. I envy you that. I'm out in California, and it's always kind of nice, which is good and bad, because then you miss things like spring and fall a lot. So it's a pleasant time to be here. Like Sam said, I gave the first part of this talk last 2 years ago, and I thought it was like an hour and a half talk, and we got through about half an hour of it, and a class came in, so I didn't get very far. So basically, it's the second half of that talk, but I've also modernized it a little bit by including some other material, basically the chaos stuff and the complexity stuff, that are things that are of interest to the Defense Department even as we speak. So basically, I'm trying to compare things that are funded right now that are not maybe in the traditional IDS category. So it's stuff that people are applying to computer network traffic, computer network defense, but it's not maybe the traditional stuff, but it is stuff that is of growing interest, I guess to say. So maybe it's unfortunately still in the advanced category, but probably not that much longer, because I think we've sort of fleshed out a lot of the virus type, signature type devices, and kind of know how that works now, and maybe people are ready to beef those up or augment those a little bit. So without further ado, cleverly titled Low Dimensional Answers to High Dimensional Questions. I thought that was really, really clever. Like would you buy a used car from this guy? It's the most jingly title I think I've ever come up with. Okay, so a little bit of history to ramp up. I was a new guy at NSA in 1998, and there we run off of things called these Presidential Decision Directives, and one that you guys are probably familiar with is Presidential Decision Directive number 63, and that was on critical infrastructure protection. And they break these things out. FBI's detailed to do this, and Department of Energy does that. And NSA was tasked at that time to do research on computer network defense. So that was sort of our piece of the puzzle to work on. Okay, so what does that mean? And like I said, our particular emphasis was on computer network defense, internet defense, and in particular non-invasive, invasive approaches. Meaning we didn't want to read people's email. We just wanted to somehow to kind of keep tabs on what was going on and watching out for the privacy of citizens. Okay, I know there's things in the news lately to the contrary, but we didn't have anything to do with that. All right, so some of the non-invasive approaches. Things from chaos, dynamical systems theory. I don't know if anybody here is much of a chaos fan or something like that. A lot of things from complexity theory, a big enclave of folks doing that out at the Santa Fe Institute in New Mexico. And other things that we've done are the thermodynamic approach, which is stuff we call Therminator. And I was going to sort of compare these three schools of thought and kind of show maybe aren't they all kind of thermodynamics in the end, and just kind of justify why we did what we did, all those years ago now, unfortunately, long time back. But still, again, unfortunately, ahead of the curve, unbelievably. Okay, so just to kind of get some language set and some concepts set, here's just a little toy network. I know you guys know the internet doesn't really work like this, but it just sort of helps us get a common vocabulary maybe to get started. So let's suppose that it's a toy network, and the only possible packets are 2 bits long. So I guess by my counting, that gives us 4 possible packets. And one friend might want to send a message to another friend. Maybe they wanted to go on a walk. So it's a pretty simple packet structure. You can't say a lot with 2 bits, but maybe they managed to send a simple message like, let's meet at 2 o'clock, and the other friend says, yes, bring donuts, something like this. Maybe they want to go for a hike or something like that. All right. So with that, we can take the 4 packets maybe and map them to the 4 directions, north, south, east, west, say. And if I do that and I look at my traffic on a network, I kind of get a picture, and I hope you can see it there, like the little blue path. Can you see the little blue path okay in the front? So I can make a connection. What I want to do here is make a connection between the data and some kind of a visual. And I want it to be kind of one-to-one. I want it to be, have the same information content in it that the bit stream does. Of course, here it's not exactly the same because once there's a loop, this is even data reduction. But I guess the point is it's no harder than the real internet traffic. Almost as hard, and there's a lot there to look at. And you can recover a lot from just looking at the picture. Okay, now you guys know real packets aren't 2 bits long, so let's up the complexity a little bit and make them 3 bits long. And maybe that allows me to say more complex things rather than not just let's meet at 2, but let's meet at the origin at 2. And now it gives me a chance to put chocolate on the donuts. So things get a little more involved. But unfortunately, so does the number of directions, the number of degrees of freedom available to me now go from 4 to 8. And the path that my traffic takes on this graph also is a little bit more involved. So we get a little bit of a trade-off. Okay, this is the biggest number that I know of. You guys might know bigger numbers, and I'm sure Professor Wagstaff knows of much bigger numbers, but has anybody computed what 2 to the 1500 times 8 is? That's the number of different types of packets you could conceivably have. It's like 10 to the 3612. That's like the biggest number that I know about. So before, when we said we had 4 directions for packets that are 2 bits long, and we have 8 directions for packets that are 3 bits long, this is packets that are realistic 12,000 bit long packets. That's a lot of different directions. So what happens when I try to look at a graph of a message now? Well, I could get something that's pretty bizarre looking. I don't know what to make of that. Again, it's certainly no harder than the actual message. It's maybe a little bit easier if you think about the loops as being sort of a redundancy. But the dichotomy here is that even though the traffic itself looks complex, maybe it's someone just trying to do something really, really simple. So on one hand, it's just a guy trying to get directions, say, to a hiking location called Birdall Field. He's trying to get in from MapQuest, something very reasonable and pretty simple and pretty understandable that a human would want to do. But if I look at it, just look at the facts, it's this horrifically bizarre, complex knot of stuff. So it's a dichotomy. The goal is to somehow bridge the gap between the two truths here. So the human can be aware at a glance of what's going on with the network traffic, and faithful representation that a human can just sort of absorb easily. Okay, so I kind of said that we've got a high-dimensional tangled mess, and we didn't go out of our way to make the problem hard. It really is. If you look at it, just matter-of-factly, it is kind of hard. I mean, there is really 10 to the 3,612 degrees of freedom. That's called high dimensional in a lot of circles. So what to do about it? So we thought there was 2 roads. One of them is ad hoc personal best, and the other one is just try to apply some science to it. So, we're all out of grad school in our class, the class of 98, incoming class NSA, and everybody wants to show how smart they are and all this kind of stuff, and guys in there are a lot smarter than me, of course, and all that's all well and good. But, the management came down and said, it's really an important problem. I want you to do the very best you can, So we thought, rather than just sort of rely on the circle of N people being the smartest people ever born, maybe we'd go out and look at outside ideas and bring in what we could from existing sciences. Many generations of people, maybe even smarter than us, gasp. So there you go. So when we did that, the sciences kind of jumped out. We're in the business of taking high-dimensional things like that network, the path of a message through that bit space, if you will. The sciences that were kind of in the business of taking high-dimensional things and making them low-dimensional were, chaos, complexity, cybernetics, and thermodynamics. Okay, so the first topic we'll touch on is chaos and dynamical systems, and you can tell it's chaotic because the letters are jumbly. That's sort of a joke. Maybe not that funny, but okay.